Hello everybody, and welcome to the top of page 14 in the workbook. We are about to enter what I'd call the second half of this section, this long section on limits. Up to this point in this section, we've talked about how to approximate limits, basically. Approximate using graphs or using tables. Okay, and that's a nice tool if you want to estimate a limit, but is there a way that we could calculate the limit of a function exactly? That's what we want to tackle now. Okay, and it turns out there's one nice theorem that we can use to calculate a limit exactly, and it deals with nice functions, functions that don't have any breaks or jumps in them. Okay, so I want to draw a picture of this situation. Okay, so over here is going to be the graph of a function. Okay, and notice that I'm drawing a smooth curve, just to kind of match the words here, no breaks or jumps. And let's suppose that the point A is here. All right, well, what would the y value of our function at a be? We don't know its specific value, but symbolically, it's customary to call that f of a, just the output that goes with the number a. Okay, and here's the question that I'd like to pose. What would the limit as x goes to a of f of x be for a function like this? Okay, well, remember what a limit is again. It's like asking you, if x gets closer and closer to a for this function, what do the y values get closer to? Okay, so we'll go to our function and pick a point that's bigger than a. That's going to put us here. And we're going to slide along our graph towards x equals a, which is going to be in this direction, right to left. Notice that we're approaching that point right there. And then we'll do the same thing from the other side of a. We chose a number that's a little bit less than a and slid towards x equals a. This time we're going to be sliding towards the right. And from both directions, we're approaching this point. What is the y value at that point? It's just f of a. Okay, and so that's the value of our limit. Okay, so kind of summed up shortly here, what this is saying is that if your function doesn't have breaks or jumps in it, you can calculate your limit by literally just taking the number x equals a and substituting it into your function. Okay, and I want to show you what we mean by that in example 3 down here. Okay, so they'd like us to use algebra to calculate the exact value of these limits, and by using algebra, they're just basically asking us to use this theorem. Okay, so for this first limit, we would first maybe make the observation that 3x plus 1 over x plus 9, if you were to graph that function, it would be nice and smooth. The only problem point would be where the denominator is 0, okay, at x equals negative 9, but our x's are approaching 2. We're a long ways away from negative 9. So the key observation here is that this function 3x plus 1 over x plus 9 has no breaks or jumps in it near x equals 2. Okay, which means that we're free to use this theorem to calculate the limit. Let's do that. Okay, so to take the limit as x goes to 2 of 3x plus 1 over x plus 9, the theorem says we can just plug in the x value that we're approaching. So we're going to take 2 and just substitute it in for our x values and see what we get. So let's see, in the numerator we get 2 times 3 plus 1, that's 7, and in the bottom we get 11, and that means that 7 over 11 is the exact value of our limit. Notice we were able to get that without looking at any graphs and without making any tables. That is the exact value of our limit. Okay, let's do one more example here. So part B would like us to take the limit as x goes to 1 of x squared minus 8x plus 7 over x squared plus 5x minus 6. Okay, if we try out the same method that we just used in part A, we would just take the number 1 that we're approaching and substitute it in for our x's. Okay. All right, my question to you is, what happens when you do that? What do we get here? Okay, well, if you do the arithmetic, you'll notice that you get 0 on the top and the bottom. Okay, both the numerator and the denominator work out to be 0. What does that mean? What do you think that means? Well, it's natural to look at that and say, oh, this limit must be undefined because we got a 0 in the denominator and we can't divide by 0. Well, you're right that we can't divide by 0, but we have to be a little careful because this limit, we're taking x is approaching 1, but it's never actually equaling 1. So we don't ever equal 0 exactly in the denominator. And so this limit could exist even though we got a 0 in the denominator when we plugged in 1. This is sometimes what's called an indeterminate form in mathematics, 0 over 0. Okay, so we need to do some further investigation to see what really happens with this limit. Okay, and let me show you what I mean. So I'm going to back up here. Okay, obviously, we can't get a number from 0 over 0, so what do we do to calculate a limit like this? Well, think algebra here for a minute. Is there anything algebraic that we could do to our function? You might notice that the top and the bottom can be factored. So x squared minus 8x plus 7, for example, factors as x minus 7 times x minus 1. Okay, and then the denominator factors as x plus 6 times x minus 1. Okay, do you notice anything that we can do at this point? Okay, well, there's an x minus 1 that's common to the top and the bottom, so we can cancel that. We can get away with doing that because x never exactly equals 1 when we take this limit. So really, we're just taking the limit as x goes to 1 of x minus 7 over x plus 6. And now, let's try plugging in 1 for x. Okay, if we do that now, we're going to get 1 minus 7 over 1 plus 6. There's no 0 denominator anymore. We took care of that problem by canceling the x minus 1, and we're going to end up with negative 6 over 7, it looks like. Okay, and that is the value of our limit. Okay, so you'll see problems like this where you may have to do a little bit of algebraic simplification before you can use the theorem to calculate the limit.